get started. Relativity, it's a beautiful topic, and what I want to do is kind of take it a little bit from the lighter side and just tell you first of all about the principles, then tell you what the good things are, the success stories of the theory. Then there is also some bad news, and there is some ugly news. And then we look at the Schwarzschild solution, something you are doing in the homework, in another setup. And then I want to talk a little bit about discrete gravity also, which is a kind of a really interesting approach and numerical at first, and has been started already in the 60s. First of all, about relativity, we have already kind of seen the math. I mean, this is heavy. Really, kind of, if you do the computation, you will actually do the computations for special cases like two-dimensional manifolds, or you can do it. You can throw in any n-dimensional metric of any n-dimensional manifold. It's just parameterization of an n-dimensional manifold, and this is what you could, in principle, test by, by computer. But it's very, very heavy. But in principle, what are the two tenets? Let's just start with Hermann Weyl. This is a kind of space-time matter. That is, we have different things. So what Einstein did in relativity, you take that together and you make a space-time, and then we have a manifold, and we have a metric which is a Lorentzian metric. So you put that all together into a four-dimensional manifold. You put that G, and everything works also in a metric which is not positive definite, but has this minus sign here. A model space-time. And then we have matter also involved, and matter interacts with the geometry in both ways. So if you give the manifold, if you have given the manifold, then what we can do is we can look at how geodesics move, right? We can look at geodesic paths.
Geodesics, and that it takes either the shortest path or the longest path. Then we know that in flat Euclidean geometry that just corresponds to a straight line. Okay? But what Einstein's theory of general relativity predicts is that massive objects warp space-time, and that by warping space-time, that gravity isn't a force, but it's just a consequence of this curved space.
And that's an equation we have seen, kind of that ij equal to 1 to 4, and then we have the gamma ijk, and then we have the x plot I and the x dot j. So these equations here tell us how matter moves in the geometry.
Proving that light doesn't need a medium to travel in. It just needs open space. So we have, from the principle of least distance and least time, that light travels in geodesics, that it doesn't need a medium to travel in. And so in flat spaces, it goes in straight lines, doesn't need anything to travel in. And so if we have a massive object, instead of traveling in a straight line, we should observe that the light actually travels in a curved path, despite not having any rest mass itself.
Then maybe the second tenet is you assume you have a manifold, and you're just actually searching for that metric is determined by matter. And about this is kind of what we have written down. These are the Einstein equations, which are without any matter, but what you have is then you have just R minus 1/2 S G. So this depends on G and this depends on G is equal to, that's what is given, is a tensor which is a mass tensor, energy momentum tensor, or mass matter tensor. So what is given here is the T, and what you actually figure out is the G. So this is an equation, a complicated partial differential equation. So there are two ways, right? We have matter moving in the geometry, and we have the geometry determined on the matter. Kind of even the ugly thing is there is nothing which combines these two, right? We assume here that the mass tensor is given in space-time. God has given you that, and then you compute that. Or And then you have this. So in principle, what happens really is that the matter here is also each of the particles in here, kind of these are curves in space-time, they are actually moving on geodesics. You look at the good, and the good is that we have quite a few success stories, and I have just written down 7.
And so let's imagine that this lens actually represents a massive galaxy, and the red dot represents this quasar that was observed in 1979, and you can see that if we get slower or closer and closer to the middle, then ultimately, how many people see a red dot on the other side? All right, so what they saw in 1979 was actually not one quasar, but 2 quasars, and then realized that what they were actually looking at was the same quasar. And what was producing the mirror image of it was a massive galaxy in the middle. And since then, they have observed not only multiple multiplicities of an object, but if you get an object that is even closer to a massive object, you can get these arcs. Or if it's directly behind the massive object, you can get an Einstein ring, where you get the light bent around that massive object, and it makes a ring, it smears out the light from an arc into a ring. And so wherever you see things like pictures from the Hubble telescope or from the James Webb telescope, where you see these arcs, that's due to gravitational lensing, and is a direct confirmation of massive objects warping space-time and bending the path of light, even though light itself does not have a rest mass. And that by warping space-time, gravity isn't a force, but it's just a consequence of this curved space. And so you can imagine that with this Euclidean geometry, if I were to draw a circle and then measure the ratio of the radius to the circumference, that I would get 2 pi in a Euclidean geometry. Or if I was to draw a triangle out and take the sum of all the angles inside, that I'd get 180 degrees. Or if I took a square, that I would have 360 degrees. The light actually travels in a curved path despite not having any rest mass itself. So